Hey guys, today we're going to learn about momentum and impulse. That's our topic for today. And this stuff is in our textbook in Unit 2 on pages 95 through 118. And what I'm going to tell you today is enough to get you started on the homework problems that you have for today, which are assigned in the classroom. So we're going to look at concepts and definitions which deal with momentum, what momentum is and what contributes to it. And then we have a couple of equations. One is the momentum equation, which is how we actually describe momentum, hang a number on that concept. And then there's another very useful one called the impulse equation, which I'll explain as we get there. So we have two math equations that we're learning today, and we're going to see how to use them. So we're going to start off with Isaac Newton because everything starts in physics starts with Isaac Newton. And Isaac Newton thought about inertia. We learned about the first law recently and about how all objects have inertia. And he was thinking on this particular day about the inertia of objects which are moving. So inertia in motion. Now, as you know, inertia is the characteristic of a thing which resists changes in its motion. So something which is stationary keeps staying stationary until something pushes it, and something moving keeps on moving until something stops it or changes its motion in some way. And again, he was thinking about things that were actually moving. So the way he was thinking about it is this idea that objects are hard to stop. Some objects are more difficult to stop than others, but everything takes some kind of force to stop it. So it might be that an object is hard to stop because it's moving fast. So like Neo and the bullets here. Bullets are hard to stop, even though they don't have very much mass, simply because they're going so fast. So the fact that something is moving quickly means that it is hard to stop. So velocity matters. Now, the other thing that can make something hard to stop is that it might just be really big. So this truck here says speedy truck, but even if it's moving slowly, we know from our common sense that we don't want to get in front of it. If it's rolling along like at 1 mile per hour, we're not going to go stand in front of it because it's going to knock us down and run over us. So it might be hard to stop simply because it's big, even though it's not moving very fast. So mass matters also. If there's a lot of stuff there, it's hard to change its motion. Now, it can also be a combination of both. So it might be big or fast or some combination. So Isaac Newton recognized that to really describe the quantity of motion, if you want to hang a number on moving objects, you have to consider the mass and the velocity. And that's what he did. He defined momentum as mass times velocity. I think I have the equation here. Yeah, here it is. Okay, define momentum. So momentum is the name that he hung on this idea of the quantity of motion. And the physics meaning of momentum is pretty much the same as the way you recognize momentum. If something has a lot of momentum, it kind of tends to keep going. If it doesn't have much momentum, it's easy to stop. But Newton figured out that you can put a number on this by this equation. P equals mv. Now, P stands for momentum. I'm not sure why. That's one of the mysteries of physics of how the letter P got used for momentum, because there's no P in there, but it is what it is. M is the mass, and then velocity is the V. So we measure mass in kilograms and velocity in meters per second. And if we keep our units consistent, then we can compare the momentum of one object with another. So, for example, I have a bowling ball which has a mass of 7 kilograms. You've probably seen it before. And if that bowling ball is rolling along at 2 meters per second, then to figure out the momentum of this, we just do 7 kilograms times 2 meters per second, and we get 14 kilogram meters per second. So 14 units of momentum. It's a very simple thing. 7 kilograms times 2 meters per second equals 14 kilogram meters per second. Now, this is one of those three-part equations. So if we have any two of them, we can figure out the third. So for example, if we were told that the momentum of the bowling ball is 14 kilogram meters per second, that would be P, and we know the mass of the ball is 7, we can figure out that the speed is 2 by dividing 14 by 7, and we get 2. Okay, so if we know any two of these, we can figure out the third. All right, let's put that back away here. Okay, so for example, if we have, well, let's see, you know what, we can just move on from that. Okay, So finding momentum of an object is very straightforward, just multiplying um, the, the mass times its velocity. But what if we want to change the momentum? How can we do this? Well, let me show you an example here. So I'm going to change cameras for a moment. Okay, so I have a bowling ball here. It has mass, and I want to give it momentum. So how do I give it momentum? Well, I have to make it move. And the way I make something move is by applying a force to it. So I'm going to kick it to give it a force. Now it's moving, and it has momentum. But there's another way I can do this too. I can also use my pointing stick, and I can push gently on the ball with a smaller force. And it slowly accelerates and it goes faster and faster, but eventually it's going just as fast as it did when I kicked it. So in the end, it has the same amount of momentum. But the first time I applied a large force for a small amount of time. And the second time I applied a small force for a longer period of time. But the combination of the force and the time resulted in the same change in momentum. Okay, so what we saw in that is that if we want to change the momentum of an object, we can provide a very large force for a short period of time, like kicking the ball, and that produces a given change in momentum. But we can produce that same change in momentum by applying a small force for a longer period of time. So it's this combination of force and time which produces a change in momentum. Now, Newton defined force times time as an impulse. So applying a force for a period of time, that is applying an impulse to an object. Impulse is not force, it is force times time. And what that does is it changes the momentum of the object which is experiencing the force. Now, for this reason, we call impulse force times time, but we also call impulse a change in momentum. They all mean the same thing. And in mathematical terms, we set them equal to each other. So force times time produces a change in momentum, right? So the word impulse means force times time, but it also means change in momentum. Force times time is how you get a change in momentum, so they mean the same thing. All right, let's look at this so here's the equation. It's all laid out for us here. Force times time equals mass times a change in velocity. So force is in newtons, as we've seen. Time is in seconds, as we've seen. Mass is in kilograms, and velocity is in meters per second. Now, you probably want to pause the video for a moment and write this down, because this is a very important equation. Newton saw this as the foundation of all of his physics. You can actually get Newton's second law, F equals ma, by just rearranging this a little tiny bit. We're not going to do that today because we don't really need to see that, but that's how it is. So this is the impulse equation, really useful, and it's one that we're going to use here. So let's move forward and try it. Okay, so suppose we have a crate sliding across the floor. It's a 50-kilogram crate, that's over 100 pounds, and it's sliding across the floor at 4 meters per second. But the floor is a little bit rough, so it slides because there's friction. It slides to a stop in 3 seconds. We want to figure out what the momentum of the crate was before it slowed down, and then we want to figure out the force that's acting against it to make it stop in 3 seconds. To do this, we're going to go to the clipboard, and here it is. So we have a 50-kilogram crate. It's rolling on, sliding along at 4 meters per second. It stops in 3 seconds. We want to find the momentum that it had originally, and then we want to figure out how much force it took to stop it, or how much force it experienced to stop it. So first, for the momentum is P equals M times V, which is 50 kilograms. That's the mass we were given, times the velocity, which is 4 meters per second. So that comes out to be 200 units of momentum, 200 kilogram meters per second. That is the original momentum, Now we want to find out how much force it takes to stop. And to do this, we're going to use the impulse equation. This is why it's very useful. So the impulse equation is force times time equals a change in momentum. A mass times a change in velocity. That means that the momentum of this object, whatever it is changing. So we can, we know that we have lost the 200 kilogram meters per second. We've lost that momentum because it has stopped. So this right here is going to be a minus 200 kilogram meters per second. And this was caused by some force which lasted for 3 seconds. So force times 3 seconds equals that change in momentum. So we're going to divide 200 by 3, and we'll go 200 divided by 3, and we get 66.7. The force is equal to 66.7 newtons. But there's this minus sign here, right? Because we stopped the thing. So that really means that the force is a negative 66.7 newtons. Now, what does that mean? Well, that means that the force was being applied in the direction opposite of where the crate was sliding. So if the crate was sliding this way to start, and then it stopped, that means that there had to be a force acting on it in this direction. And that's what this minus sign means. It just means that the force was acting against the motion of the crate, and that's what made it stop. You got to push against it to make it stop. Okay, so in this case, we figured out the change in momentum, and then figured out how much time it would take. Now, we can also just kind of skip this first step. We can also skip this first step and just use the impulse equation right from the word go. So we can say force, that's what we're trying to figure out, times 3 seconds, because we have the time, is equal to the mass, which is 50 kilograms, times the change in velocity, which is going to be minus 4 meters per second, because we're slowing it down. Okay, and when we work it all out, we wind up with the same answer, negative 66.7 newtons. Now, the negative sign, don't get too bent out of shape about that one. If you just keep in positive numbers, this will tell you the magnitude of the force, and you can look at it and say, oh, well, the force had to be going that way to make it stop, and you get to the same place. So don't worry too much about the negative signs on this. What we're mostly worried about is the number, the 66.7. Okay, let's look at another one here. Suppose that we have a bowling ball, all right, and it has a momentum of 300 kilogram meters per second. That's 300 units of momentum, and it stops in 15 seconds. We want to figure out the force that is acting on the ball to make it stop. And again, we're going to use the impulse equation. Force times time equals a change in momentum. And in this case, we don't know the force, but we do know that it lasts for 15 seconds. And it's going to make a change of minus 300 kilogram meters per second. So we're going to divide both sides by 15. 300 divided by 15. And it turns out to be force is equal to 20 newtons. So if we apply 20 newtons of force for 15 seconds, we'll get that change in momentum. Okay? All right, let's go back to our slides here and look at some more stuff. We've got a couple more examples for you to run through. Okay, now I want to get this idea of impulse here illustrated in another way. We'll get away from the math for just a moment here. So let's move my picture up here. That's a better place. And imagine we have an airplane that is on a runway, okay? And it's going to take off and go flying. And when it's flying along, we're going to say that it has 10,000 units of momentum while it's flying along, because it's moving. You know, airplanes move as they go through the air. So let's take it back to the runway, and it's just sitting there. Its initial speed at first is 0. It hasn't started its takeoff roll yet. So now we push the power up and we make a lot of thrust from the propeller turning, and it starts rolling down the runway, slowly going faster and faster, because the propeller is exerting a force on the air, which is pushing back, and it's pushing, basically the propeller is dragging the plane forward. It's exerting a force on the plane. So that little force lasts for a long time. It goes faster and faster and faster and faster, and pretty soon it's going fast enough to go flying, and it flies up, and yay, he's flying along, and he's going fast, and he's got 10,000 units of momentum. Fantastic. So we had a small force that lasted for a long time, and it produced this much momentum, 10,000 units of momentum. Now, on this particular day, the pilot's not paying attention, and he hits a mountain, crashes into a mountain. We'll say that he sees it at the last moment and ejects and comes down safely in his parachute. But the airplane crashes into the mountain, and it goes from moving really, really fast to not moving at all in the snap of blink of an eye, snap of fingers. Now, in this case, we have the same change in momentum. We have the same impulse occurring, meaning that a change of 10,000 units of momentum. During the takeoff roll, we went from 0 to 10,000, and during the crash, we went from 10,000 to 0. So the change is the same. But when it hit the mountain, it was a huge, gigantic force that was very, very short, lasted for a very short time. And that force was so great that it destroys the airplane, breaks up into little tiny pieces. So here we have a small force which the airplane can survive, and it gradually goes faster and faster and flies, and everything's great. At the end of the flight, when it crashes, it has the same impulse, but it's caused by a huge force for a very, very short period of time. But it produces the same change in momentum. Okay, let's finish up with a couple questions here so you can practice this stuff. Here we go. So there's these three problems, and what I want you to do is pause the video and work these out for yourself, all right? Now, the first two are the same situation. We have a truck hitting a tree and stopping, and first we look at what happens to the truck, and then we look at what happens to the driver. So this is the driver of the same truck, which means the driver was moving as fast as the truck was, if you're looking for speed in part two. And then the third one here is its own little problem. So pause the video, find answers as best you can, and then start it up again, and I'll show you the solutions to the setup. So do the best you can. If you get stuck, then you can look at this. So let's go back here. I'm going to show you the answers right now. And here we go. This is it. For all of these, we use the impulse equation. This is the first one, half a second, 1,000 kilograms for the truck. It loses 5 meters per second. This comes about to be the force. This is the driver. The driver experiences 5,000 newtons of force in only 1/10 of a second because he hits the steering wheel. He's not wearing his seatbelt. And he also slows down by 5 meters per second. And for this, we can figure out his mass. And then finally, this is the one with the hockey puck. 40 newtons of force, asking for 2/10 of a second, acting on 1/10 of a kilogram. And it turns out that it has a change in velocity of 80 meters per second. Okay, so that's what we got. That should be enough to get you going easily for all the questions that you have in the back of the book. They're actually not as difficult as these, so make sure you know how to do these. These are useful, and we will see you next time.